Princeton, and a BS from the greatest program in the world, Michigan Tech. Of course, no bias there at all. Prior to joining Auburn, she was Geochemical Postdoctoral Fellow at Lawrence Berkeley National Laboratory. Her expertise and interests are in understanding water-rock interactions in environmental systems, particularly in subsurface energy systems, including geologic CO2 sequestration and compressed energy storage. Her laboratory is currently supported by NSF, including a 2019 Career Award, congratulations, ACS PRF, and DOE. So without any further ado, Lauren, you could go ahead.
All right, let me see if I can share my screen with you. Okay. Well, thanks so much for having me. It's a pleasure to be there virtually. I put my northern lights on to try to channel the northern Michigan memory. It's my pleasure to share with you some of the work we've been doing, trying to enhance understanding of mineral reactions in porous media, as well as the evolution of reactive permeability. So, as you're probably aware, atmospheric emissions of CO2 continue to increase. And if we take a look at where those emissions are coming from, we can see they're predominantly from means of producing energy, so coal, oil, and gas. And that emissions from these sources are increasing as well. Now, here is the CO2 intensity for various means of energy production, where you have processes that are really CO2 intensive at the top of the plot, and then processes that are less CO2 intensive at the bottom. And so if we want to think about how we can transition ourselves from relying on these really CO2 intensive means of producing energy, we need to transition to means of less CO2 intensive energy production. And some of the things I'll talk about today, right, is how we can do that with coal-fired power plants using carbon capture and storage, but then also increasing our reliance on renewables, for example. And so my work in general falls into understanding geochemistry in these subsurface energy systems towards helping us decarbonize energy production. And so this is geologic CO2 sequestration, as well as using CO2 for energy storage, like the picture on the right here depicting renewable energy storage, and then also geologic nuclear waste disposal, and then how we can reduce water use used for energy production, so things like CO2 enhanced oil recovery and CO2 fracking. The approach that is used in my group couples imaging with experiments and numerical simulations. So we use multi-scale imaging to try to understand the pore structures from nanometer to core scale, especially those properties that are important for flow and reactivity. And then we use laboratory experiments that mimic the environmental conditions. So could be high temperatures and pressures. And then try to use this information to develop numerical simulations from the sub-pore scale to continuum scale to understand what's going to happen over longer time scales beyond what we can mimic in the laboratory. I don't have time to talk about all the things that are going on in the group, so I just wanted to briefly tell you about some of the highlight areas, and then we'll talk more in detail about a couple of them. So we have a current project trying to understand the role of mineralogy in controlling fracture formation, particularly for CO2 enhanced oil recovery. A new project that just started in September, where we are looking at using 3D printing to fabricate reactive rock samples. And then an interdisciplinary project that's funded by the Auburn Presidential Awards for Interdisciplinary Research, where we have gathered faculty from across campus, and we're trying to develop a CO2 utilization and storage center to serve as a resource for the Southeast as we transition away from letting CO2 be a waste product in the atmosphere. And then I'm going to touch on this project that we are trying to understand accessible mineral surface areas as a means to improve simulation of reaction rates in porous media. And some of our work looking at porosity and permeability evolution as it applies to reservoir site selection for CO2 sequestration, which is part of a large DOE partnership in the Southeast called CCARB. The other thing I wanted to mention is we have a new instrument that's supported by NSF MRI. We just got over the summer. That's Xray Nanotomography. And this is open to external users, so I'm trying to start advertising it. But this is really kind of a cool instrument that allows you to take 3D images of samples. And the voxel sizes here range from 100 nanometers and up. And your samples can be as large as 30 centimeters. We also have some in situ testing stages in this instrument that really make it one of a kind in the US, where we have heating and cooling testing as well as tensile and compression testing. And there's just a couple example images on the right here showing you some of the high resolution images of our shale samples. Okay, so let's start talking about how we currently model mineral reaction rates. So usually we use a rate law like the one that's shown here that's based on transition state theory. So basically the dissolution rate of the mineral is proportional to a rate constant, a thermodynamic component, and the reactive surface area. Well, we have a pretty good understanding of the thermodynamic component and the rate constant. We have a really poor understanding of this reactive surface area term. In fact, if you gather reactive surface area values that were used in prior simulations of CO2 sequestration, and I've plotted them here, you can see that we have really large variations in the surface area values that we're using. And since this is directly proportional to the rates in our reactive transport simulations, you can see this is going to be a challenge. So why are the values so large? Well, let's talk a little bit more about how we're getting these values. So the simplest approach is to use a geometric surface area where you say that everything is a sphere of a single grain diameter. Well, the problem with this is that clay minerals are inherently different than other minerals and have much larger surface areas. We account for this by using two surface areas, one for clay minerals and one for all other minerals. However, this is also an oversimplification because we know that real mineral surfaces are not perfectly smooth. They have some amount of surface roughness. So we can account for this by applying a roughness factor. This is typically a value of 10. This rough surface area can also be measured in the laboratory with a BET analysis. The challenge here is that we have seen some evidence in the field that only some sites are potentially reactive. So we account for that by applying a scaling factor. This can be anywhere between 1 to 3 orders of magnitude. And this is an effective surface area. This scaling factor is sometimes also applied directly to the geometric surface area. And so now you can see we have a huge range of potential surface area values that we've estimated to use in our numerical simulations. The problem with this estimate is still that mineral abundance might not accurately reflect accessibility in porous media, as well as this does not account for the fact that surface areas might actually be changing as reactions progress. In some of our recent work, we have used a multi-scale characterization or image-based characterization approach to actually quantify the accessible surface area. So we combine 2D SEM imaging with 3D FibSEM imaging of the clay minerals, so the nanopores here, try to understand the accessibility of mineral surfaces to the reactive fluids. We can account for connectivity in 3 dimensions with X-ray CT imaging and actually quantify mineral-specific accessible surface areas. We have validated this using a core flood experiment, mimicking conditions from the field site, and then used reactive transport simulations to evaluate the performance of these surface areas. Here you can see the experimental results from the core flood are in these red squares, and then this set of simulation results in the solid lines, where basically we're using a surface area that assumed all the mineral phases were accessible for a reaction, and this really overestimated the reaction rates. Then if we use our image obtained accessible surface area, we're able to effectively capture the reaction rates in our core flood experiment. And so what we wanted to know then is what is the impact of image resolution on these properties we are extracting to build our reactive transport simulations. So namely the volume fractions and accessible surface areas. And then if we do have variations with image resolution, what kind of impacts are we having on our simulated mineral reactions and reaction rates? And this is work that was done by my PhD student, Fanchi Quinn. We are going to look at a sample from the Paluxy Formation. This is from a potential CO2 storage plant in Kemper County, Mississippi. Here we used SEM Imaging to enhance our understanding of the pore structure at high resolution. We can get porosity information for this sample as shown in the segmented image on the right. We can then combine this with EDS imaging, which provides elemental maps to understand the distribution of minerals within the sample. So in this image, each color corresponds to a different mineral phase. And so this particular formation is really rich in quartz, but we also have some more reactive phases like calcite present, as well as some feldspars and clay minerals, or the clays are shown in yellow. We then repeated this process for images with resolutions from 0.3 microns to 5.7 microns, and then processed the image to quantify mineral abundances, accessibilities, and accessible surface areas. In terms of abundances or volume fractions, what we found is that there was really little variation in the volume fractions with changing image resolution. We then wanted to understand where the fluid would flow, so we quantified the pore connectivity. So you can see connected porosity in pink and unconnected pores in black. So you can see a lot of the pore space is connected, but we do have some unconnected porosity in the sample. And then we can quantify that, where we saw some variation with image resolution, but no overall trend in terms of increasing or necessarily decreasing with resolution. We can then quantify what the accessibility of these different mineral phases are, where that is telling you the accessibility to where the fluid's going to flow. And what we noticed is that with decreasing resolution, we had a decrease in the accessibility of smectite and an increase in the accessibility of quartz. And oftentimes this, the smectite is present as a coating on the quartz mineral surfaces, for example. And if we take a look, just to give you some examples here, we have some close-ups of these small scale features that are really challenging to capture with lower image resolution. So on the left, you can see a muscovite grain, whereas you can see in the highest resolution image, you can really understand the pore structure within the layers, but you cannot see that all in the lowest resolution image. And then on the right, down here on the bottom, is a close-up looking at some of this smectite illite, where you can see the pore structure here really starts to distort as the image resolution decreases. We also accounted for pore connectivity in 3 dimensions using our 3D Xray CT imaging, and then use that to quantify accessible surface area. And so what we saw is that you have an increase in the accessible surface area of quartz with decreasing resolution, and decreases in the accessible surface area of potassium feldspar and calcite. But one thing to also notice is that these variations are less than 1 order of magnitude. And so the high resolution image, right, takes more time and more computational power to process compared to the lower resolution image. So we were curious if this is going to make an impact on the simulated mineral reactions if we are going to use this information to construct a reactive transport simulation. So in our model, which we built in CrunchFlow, we are going to simulate the flow of CO2 saturated brine through the mineral cell under the field conditions with elevated temperature and pressure. We're going to track the evolution of mineral volume fractions, surface area, and porosity. And we're going to look specifically at 2 timescales, show a short timescale of about 2 weeks, which reflects maybe what you'd see in the laboratory, and then what would happen at the field site over 20 years. In terms of surface areas, we're going to use simulations or build simulations using our accessible surface areas obtained from the lowest and highest resolution images, as well as look at what if we had used surface areas from those other approaches. So from a geometric surface area, which are typically higher, 1 to 2 orders of magnitude higher than the accessible surface area, and then the BET surface area values, which are even higher than the accessible surface areas. Let's look at the results now for the imaging-based simulations. So this is the evolution of mineral volume fractions. We have the short time scale on the left and the longer time scale on the right. At a time of 0 is when the CO2 saturated brine enters the mineral cell. So this is the background conditions. And then the simulation results using surface area from the high resolution images are the solid lines, and the lower resolution images are the dotted lines. So we see with the introduction of CO2 saturated brine, you have rapid dissolution of calcite. You also have dissolution of siderite, but you'll also notice that the variation in the simulation results using the surface areas from the high and low resolution images is really minor. If we look at longer time scales, we start to see dissolution of smectite and precipitation of quartz. And there is some slight variation in the simulated extent of quartz precipitation depending on the surface area value that you used. But overall, the variations in volume fraction due to different surface areas is pretty small. What about the evolution of porosity? So here we have porosity evolution, and you can see a rapid increase in porosity due to dissolution of the carbonate mineral phases at early times, but there's very little variation in the simulated results between the two surface areas. At longer times, we start to have an eventual decrease in porosity due to quartz precipitation, and you get some slight variation in the evolution of porosity depending on surface area. In terms of the evolution of surface area, again, we have the short-term simulations on the left and the long-term on the right. We can see the evolution of surface area mimics the evolution of mineral volume fractions. So surface area starts to decrease as the volume fractions decrease. There's really little difference in the surface area evolution of the two simulations. At longer time scales, you can see an increase in quartz surface area due to precipitation, and then decreases, for example, with muscovite as muscovite starts to dissolve. That was not as evident necessarily in the volume fraction. The evolution of surface area kind of mimics each other, where, for example, with quartz, they are parallel to each other, but really, the same kind of pattern is emerging here. Now let's compare with the simulation results using those other surface area approaches. And so there's a lot of information on this slide, but I'll walk you through what I want you to get out of it. So on the left here are the simulation results we were just looking at using the image obtained accessible surface area for short times and long times. And then over here, we have the simulation results using those other 4 surface area approaches over short time scales on the left and the long time scales on the right. And so the first thing I want us to take a look at is siderite. So siderite's in pink, and we can see in the shorter time scales that variations in surface area can result in differences in the evolution of siderite. In particular, when you're using a BET surface area, you have complete consumption of siderite within 40 hours. You'll also notice that this geometric surface area that uses a scaling factor agrees pretty well with our image-based simulation results. And then in terms of the other mineral phases, at short times, we don't really have anything happening, but over longer time scales, you can see the evolution of minerals does vary widely, where you have increased smectite dissolution with larger surface areas, increased quartz precipitation, and then some simulations also show consumption of potassium feldspar. And so you can get really different results in the evolution of mineralogy depending on the surface area that you're using. Now, in terms of understanding how this impacts porosity, we can see the simulation results from using the image surface areas on the top and the results from the other simulations on the bottom. At the shorter time scales, we have an increase to about 33% with really little variation in the different simulations. But at longer time scales, we can see the evolution of porosity can be quite different. In some cases, you end up with quite large increases in porosity before larger decreases. And then kind of thinking about these longer time scales, some of those variations are quite extreme. So to kind of summarize what we found from this investigation is that it really depends on what kind of phases you have in your system, as well as the time scale that you're interested in. So if you're interested in what's happening like at this laboratory time scale, the short time scale, we really saw variations in the most reactive phases, which were the carbonate phases here. But if you want to know what's going to happen at the longer time scale, it doesn't really matter what the surface area value was that you're using for the carbonate phases, but it did matter what was happening with these more stable phases that start reacting over longer time scales. These phases, again, the surface area had little impact on what was happening at short time scales, but did have some large variations as you're approaching like the several years time. So in terms of the properties you're going to get from the images to build your reactive transport simulation, there was little variation in the mineral volume fractions. We saw some variation in accessibility and accessible surface area. But actually, even though we had these variations, they were within one order of magnitude, and they had really little impact on the simulated mineral reactions and reaction rates. We also saw in this case that the geometric surface area that applied a scaling factor of 10 actually agreed really well with the image-based simulations. I should note, though, that there is little guidance in terms of picking the scaling factor. So we arbitrarily chose a value of 10, which is the accepted approach to picking a scaling factor. So if you picked a different scaling factor, that probably wouldn't be the case. But we also saw that it might not be necessary to use this kind of time and resource intensive approach to quantify the surface areas in all cases. So if you want to understand what's going to happen over short periods of time, you really need to have a good understanding of the surface area for the most reactive phases. And if you want to know what's going to happen over several years, you need to understand the surface areas of the less reactive phases for us, like the clays and feldspars. Some of the things we are still have ongoing in this area is trying to predict the surface areas based on composition. So this takes a lot of time to process the images and get this data. So we are trying to see if there's any predictive capabilities based on properties that are commonly or easily measured. And then trying to understand how accessible surface area will evolve as the reactions progress. Now, in the simulations I just showed you, those were done at the continuum scale. So basically, if this was what you're envisioning, like that image, this is a single grid block. But in reality, we know that the mineral dissolution and precipitation reactions are happening at the pore scale. And we've seen that these reactions can impact the pore scale and occur in a variety of patterns. So in some cases, we have seen that mineral reactions occur uniformly on all grain surfaces, like shown in red here. We've seen other systems where reactions occur preferentially along a flow path, like in channelized flow, shown in purple. In other cases, only some mineral surfaces are impacted. So if you only have some reactive minerals, or if minerals preferentially precipitate on like mineral surfaces, like shown in green. And then in some cases, where mineral reactions are controlled by pore and throat sizes and occur preferentially in small or large pores, or are inhibited in small or large pores. And you can imagine that these variations in the spatial distribution of reactions might have different impacts on the permeability evolution of the system. And the way that we currently estimate permeability evolution is using an empirical relationship like the one shown here. So these basically say that for a given change in porosity, you have a given change in permeability. And the challenge with these relationships is they're not able to reflect non-uniform structural modifications. So the fact that one change in porosity might result in a different permeability value, for example. And so what we wanted to know is that what is the impact of pore scale mineral dissolution and precipitation reactions on porosity and permeability, where these equations are just looking at the continuum scale change in porosity, for example. Our approach here is to use pore network modeling. So we develop a pore network model of our porous media based on the pore and throat size distribution and connectivity. Here we have a system of pores defined on a regular cubic lattice connected to other pores by pore throats. At the pore scale, we can apply Poiseuille's law and solve for the pressure in each node. And then at the continuum scale, apply Darcy's law and determine the permeability of this network. You can also simulate reactive fluid in this system, for example, and look at how that might be changing. What we are doing here is going to use our pore network model and try to understand the variation in permeability as the spatial distribution of mineral reactions changes. So from reactions being uniformly distributed on all surfaces to randomly distributed, only impacting a fraction of the pores and pore throats, and then occurring preferentially in or being inhibited in small and large pores and pore throats. The work I'm going to share with you today was done by my undergraduate researcher, Jacob Benzinger. And then from our pore network model, we also wanted to know, do these empirical relationships accurately reflect the evolution of permeability given these variations at the pore scale? We're going to use the same sample as with the last work I talked to you about using the Paluxy sandstone from Kemper County. Here we used CT imaging to understand the pore structure, where we can get the pore and throat size distribution, as well as pore coordination or connectivity, where you see an increase in coordination with pore size. And then we use that to construct our model. And so what we have done is run 1,000 simulations for each sub-scenario. So if we look at the initial or unaltered permeability, this is using the pore and throat size distributions and connectivity that we initially measured, and we have 1,000 simulations, and you're seeing the resulting porosity and permeability for those simulations. We then can reflect dissolution occurring by increasing the pore and pore throat sizes, and precipitation by decreasing pore and pore throat sizes. On the top here, we have looked at uniform reactions occurring. So those are occurring on all pores and pore throats, and altering those pores and pore throats by an extent relative to their initial size. And you can see that this results in an increase, or dissolution results in an increase in porosity and permeability, and precipitation results in a decrease in porosity and permeability. We also have those macroscopic porosity permeability equations I'm showing on these plots as the black lines. So in this system, you'll notice that this Verma-Perus 1 equation is actually able to reflect what's happening at the pore scale with the uniform reactions. On the bottom, we have a different uniform reaction scenario where now the reactions are occurring as a uniform thickness or as a uniform coating. Dissolution still results in an increase in porosity and permeability and precipitation, and a decrease in porosity and permeability. And this is once again captured pretty well by at least some of the macroscopic porosity permeability relationships shown here. So basically everything besides the Verma-Perus 1 equation. Now if we look at the random reaction scenario, so this is basically if only some of your minerals are going to be reactive. And we vary the fraction of reactive minerals from 10 to 90%, and then the extent that they were altered by the reactions. So looking at 10% alteration on the top and 25% alteration on the bottom. And you'll notice that this looks really similar to one of our uniform reaction scenarios where dissolution results in an increase in porosity and permeability, and precipitation, a decrease in porosity and permeability. And these are both captured well by the Verma-Perus-Swan equation. Now if we look at some of the size-dependent reaction conditions. So here we are considering scenarios where reactions occur in the smallest pores and pore throats at the top, and those we defined as less than the average pore size of 25 microns. And in this case, you have an increase in porosity with more rapid increases in permeability due to dissolution, and precipitation results in more rapid decreases in permeability compared to the other scenarios. You also notice that this isn't really captured that well by these macroscopic porosity permeability equations, particularly for precipitation. If we look at the opposite scenario, so where reactions are occurring in the largest pores and pore throats, so those larger than the average size of 25 microns, you can see dissolution results in increases in porosity with little change in permeability, and precipitation results in decreases in porosity with little changes in permeability. And this is not captured at all by these macroscopic porosity permeability equations. In this simulation, now we are thinking about reactions that initiate in small pores and pore throats or in large pores and pore throats. So on the top, the reactions initiate in the smallest pores and pore throats and then extend to impact pores of larger sizes. So initially, when the reactions are occurring in the smallest pores and pore throats, you have really little change in porosity. And then you start to, little change in porosity, but big changes in permeability. And then you start to impact permeability only once you start impacting larger pores and pore throats. And this is really not captured well at all by these macroscopic relationships. When reactions are initiated in large pores and pore throats and then extend to smaller pores and pore throats, you have large changes in porosity due to dissolution and precipitation. And then once you start impacting the smaller pores and pore throats, you start having increases in permeability due to dissolution or decreases due to precipitation. And these are not captured either by these macroscopic porosity permeability relationships. Now what we have shown on here in these red lines is a modified Verma-Perus equation developed in this paper from 2019 with my graduate student, Jeffrey Steinwinder. And we see that this new relationship we've come up with for porosity and permeability actually is able to reflect what we are seeing in these size-dependent reaction scenarios with reactions initiating in either small or large pores and pore throats. So now let's go back and talk about the site that we're interested in. So this is a potential CO2 storage site. And some of the things we want to know is that once reactions start occurring after you inject CO2, like we saw in the first system, and you have changes in the porosity that are due to mineral dissolution or precipitation, what's going to happen to the permeability? So the initial permeability of the site is shown here as this red star. And we know from our earlier simulations, the fraction of reactive minerals in this site is 23.6%. Now those are not all going to react right away like you saw in the simulations, and maybe only a fraction, or some of them are going to be pretty slow. But as those minerals start to dissolve, what's going to happen to permeability? So basically we've taken the results from all of our simulations and are showing them here. And you can see as minerals start to dissolve and porosity increases, you have a large potential permeability or resulting permeability. So anything from about 1,500 to 8,000 millidarcies. Precipitation, on the other hand, there's less variability, but still some, a pretty wide range of potential resulting permeability that could happen as precipitation occurs. And, the other thing I should mention is that just because you have reactions happening uniformly in one place, they could still occur non-uniformly someplace else. So from this work, we saw that the evolution of porosity and permeability depends on the spatial reaction pattern of mineral dissolution and precipitation reactions at the pore scale. and that for a given change in porosity, there's really a wide potential resulting permeability. And that makes using these macroscopic porosity permeability relationships really challenging because we're not able to reflect what's happening at the pore scale. And this was particularly true when the reactions were related to the size or controlled by the size of pores in pore throats. We've done some other related work to this, looking at what about variations in pore and throat size distributions. So this was done by my master's student, Jeffrey Steinwinder. We looked at an Alberta Basin sandstone shown here, and then several synthetic pore and throat size distributions, kind of just seeing if the shape of these distributions changed, how would that impact the evolution of porosity and permeability? And we found that qualitatively, these pore and throat size distributions don't really impact porosity and permeability evolution for most scenarios. But if you did have a sample that had really few small pores and pore throats, such as this synthetic left skew distribution, there's going to be less potential for clogging, and overall those porosity permeability relationships are going to work better. In this paper, we also developed this modified Verma-Pruss porosity permeability relationship that did work well in the size dependent reaction scenarios, and what was plotted on as those red lines on those last plots there. We're currently trying to understand porosity permeability evolution in systems where you have simultaneous mineral dissolution and precipitation. So in the results I showed you, either dissolution or precipitation was happening, but in some cases you have both of those happening at the same time. And so this is work that my current undergraduate researcher, Molly Sabo, is doing. And in these simulation results, she's looking at what if you have a zone where mineral dissolution occurs and mineral precipitation occurs that is aligned or perpendicular with the flow direction, and looking at various extents of those reactions. And what we find is that this results in an increase in porosity, but a decrease in permeability. So basically, even though you're going through a dissolution zone that would increase those, you are constricted by flowing through the precipitation zone that has decreased the pore throat sizes. Again, we have these macroscopic porosity permeability relationships shown as the black lines, and you'll notice we're not able to capture this at all with these relationships. We also considered, what if you have dissolution and precipitation happening randomly throughout the network? And in this case, you get an increase in porosity with really little change in permeability. And that, so basically, even though you're constricting some of the pore throats, you're maintaining enough of the larger pore throats that your permeability is not impacted in this system. You also notice, though, this is not captured with our current means of estimating permeability evolution. And so with that, I would like to acknowledge the efforts of my research group and the students here who have contributed to this work, as well as support of the funding for the work that I shared with you today. I'd also like to say I'm currently recruiting PhD students. If you're interested or know anyone who might be interested, here's my contact information. And I'm happy to take any questions, and I'll leave you with this image that was featured in the Art of Science exhibit last year that another one of my undergrad researchers, Parker Satterfield, put together, featuring the Paluxy sandstone. So thank you.
All right, thanks so much, Lauren. Any questions from anybody?
I have a question, Lauren. This is John Gerke. Are you coupling geochemical models with your precipitation dissolution models? I'm interested in as example would be clogging around a well screen as a result of the pressure reduction of pumping and the mineral precipitation that is common around well screens, and you can forecast not only the precipitation, but the reduction and permeability.
Sure. So the simulation results that I showed you here don't have geochemistry. They're just looking at physical changes, but you could certainly easily incorporate the geochemistry. So what we've done is take observations from the literature, like basically the resulting Peckel and Dam Kohler numbers that would result in these different spatial distributions of reactions, and use that as our inspiration for the reaction patterns. But yeah, you could certainly do the same thing, including like what is the time component, where our time component is more like looking at variations in extent as it relates to time. But this way, you know, we're not constrained to a particular set of reactions, but it's more applicable to a wider range of reaction patterns. But yeah, you could certainly use that approach to do what you're talking about with a specific chemistry in mind.
I had a question too. So can you talk a little bit about the practical ramifications maybe of some of these results? Do you think carbon sequestration has promise and not? Is it realistic? Do these results help us on that? Or talk to that a little bit if you don't mind.
Sure, yeah. Carbon sequestration is very promising. We have a large range of potential places we can put CO2 and potential storage formations. So the work I shared with you on the Paluxy site, that's a saline aquifer, but we can also use depleted oil and gas reservoirs. There's really huge storage volumes across the US, but also across the world that we can target for this. And a lot of those are also well aligned with the point sources. Actually, I don't know if I have these pictures in here. Let me see if I do. Well aligned with point sources as well. Let's see. We have a pretty good understanding about what's going to happen at over various time scales in terms of the mineral trapping. Here, maybe I'll put this. You can probably still see it. So, you know, there's been a lot of research trying to understand the trapping mechanisms. Where you put it is very important. So we're going to initially rely on having some kind of low permeability cap rock to stop buoyancy migration. But then over time, geochemistry is really going to play a large role. So what we are interested in our work is in understanding this mineral trapping, where on this slide you have some of the example mineral reactions that would be happening in these systems. And basically once you have precipitation of a secondary mineral phase, like a carbonate phase shown here on the bottom, you know, this is a permanent means of CO2 storage. So that is not going to go anywhere. It's going to be permanently trapped unless you have, you know, more significant changes in the geochemistry of the system. But at that point, it's secure. It's not going to be migrating. These other trapping mechanisms, right, that CO2 can still be mobile. There are some of the things you might be worried about would be leakage, and that could be through like a fracture. But we actually, you know, we're still trying to understand like how those fractures will evolve and how likely it is for there to be a fracture. But these formations are very far beneath the Earth's surface, so like about, you know, over a kilometer. And so you're going to pick one with this stratigraphic trap, but there's going to be several other confining layers between that formation and the surface. And there was some recent work that did some statistical estimation of the percent of CO2 to be trapped that came out in Science, I think last year, and they found, you know, like 90% of the CO2 would be trapped, even accounting for the risk of potential leakage through fractures or abandoned well bores, for example. So it's a very promising technology. We've already proven that we can do it. We are doing it at the pilot scale, and now efforts are looking to do this at the larger scale. So like the Kemper site, for example, is trying to do this at the commercial scale, but it's also something we've been doing worldwide for at least 10 years now. So this is, I know a lot of people aren't familiar with it, but it's very promising means of transitioning you know, from coal-fired power plant to those other means of producing energy that are less CO2 intensive. It's also something that mimics what's happening naturally. So this, you know, the CO2 being stored in the geologic reservoirs is a natural process, and we're just mimicking that by injecting it into these other formations.
All right, we got 4 or 5 minutes left. I want to open up to the students. Usually the professors ask all the questions, so let's have some students ask questions if you have any.
I have a question. My name is Karar. I'm a PhD student. So what is the resolution for the 3D imaging, maximum resolution that you can capture?
Sure. So with our new instrument, you can get voxels that are 100 nanometers. So the resolution is really tied to sample size a lot of the time and depends on the sample that you want to look at. So if you want to look at an entire sample and it's larger, you'll have lower voxels. If you just want to look at part of it, for example, you could look at 100 nanometer voxel size. So it really depends. So like in this top image here, we're looking at our entire sample, and so it's not as high resolution. But then if you look at just part of that here on the bottom, right, this is a much smaller sample size, or you can even look internally. You don't have to have a smaller sample size per se to get the higher resolution. So it just depends on what you're trying to get out of the image, what kind of information. But as high of resolution as 100 nanometers.
Thank you.
Mm-hmm.
Any other questions from the students? Okay, I have another one. So how would hydraulic fracturing that's going on now and perhaps the seismic activity caused by that influence any of the carbon sequestration work, do you think?
So fracking, the way we currently do fracking is with water. And this is actually not a great approach because you end up with a bunch of contaminated water at the end. So one of the things we're interested in is using CO2 as the fracking fluid. This is actually more beneficial because CO2 is a lot less reactive than water. You can also extract more of the gas because it's miscible with CO2. But then when you're done using it to create the fractures, you can leave CO2 in these low permeability formations. And so that's just another type of formation where you could have CO2 stored. One thing that is challenging is understanding if you do have a fracture and it is a reactive system, like is in the cap rock above one of these saline aquifers, is what's going to happen in terms of geochemistry. So if you have a fracture and you're flowing acidified brine through the fracture, is it going to open up and you have a larger flow path, or is it going to seal because there's some kind of confining pressure, or maybe you have precipitation of secondary minerals? And that's really something that is not well understood yet. We're trying to understand that in my group by trying to understand where fractures form in relation to the mineral phases. So if your fracture surface is predominantly really reactive mineral phases, or if it's more of these non-reactive mineral phases, and then how that influences the evolution of the fracture in terms of being self-sealing, or if it will be enhanced by the flow of the reactive fluid.
Yeah, great. A lot of unanswered questions. So you have a lot of research to do for the rest of your career. So that's
Yeah.
good. We always need unsolved problems to work on, right? So
Yeah, definitely.
well, it's 10 till. Anyone who needs to go for time reasons is fine. Anyone who wants to hang around and chat more with Lauren is welcome to do that too. I'm going to turn it over to Dave Watkins, who has some probably additional questions and students. So thank you so much, Lauren. I really appreciate your time and your effort to come and talk to us. So thank you very much.
Thank you. My pleasure.
Audra Morse also says, thanks, Lauren. I guess I wanted to tell students who maybe joined a couple minutes late that we had invited Lauren to campus, or she was planning to come in April and then unfortunately had to change her plans. So we're very happy she could join us online here, and we're still hoping to get her to campus as soon as travel restrictions are lifted. We'll see what her schedule looks like. So I just thought if students have any questions, certainly about Lauren's work or even her career path, what she did after she graduated from Michigan Tech, we could have a little bit of time for discussion here.
Hi, my name's Abby. I'm a master's student, and I just had a question about some of the modeling that your team is doing. Is it all modeling that you guys are creating from scratch, or are you using previous models and adapting them for your research?
So it really depends on what it is. So the reactive transport simulations, we're using CrunchFlow. This is a code from Carl Stiefel at Lawrence Berkeley National Laboratory. It's pretty adaptable. You can do a lot of different things with it, but it's a continuum scale reactive transport model link system. The Pore network models we created using MATLAB. So those are just something that we created in-house. So it kind of depends on what it is, but we do a little bit of both depending on what we're trying to do. With the reactive transport simulations, I really like CrunchFlow because these can be quite complicated systems. You have a ton of different possible reactions happening. You also have to look at the evolution of each individual ion species, right, to understand if you're going to have dissolution or precipitation happening. So this is a great tool for that purpose. So it kind of just depends.
Any other questions for Lauren? I guess I had one more. Can you just say a little bit about compressed air energy storage?
Sure.
And maybe what your work says about that technology. I'm curious about the, unique considerations due to the frequent cycling of pressures in the formation.
Sure. Yeah. So, and the compressed air energy storage systems, basically, this is a way that will provide potential long-term, large capacity energy storage, particularly from renewable energy. So here, when you have excess energy, you can inject some kind of gas phase into a geologic formation. And then when you need to recover energy, you can take that gas phase out and use it to drive a turbine and recover your energy. You can have storage here on a period of hours or months. What you're using to inject could be air, it could be CO2, it could be nitrogen, methane, hydrogen, some mixture of those things. Some of the things that we have done trying to understand this is trying to understand what are the properties and advantages of using these different phases. And then particularly, what if we are going to use CO2 as this gas? And this could either be as the cushion gas. So before you start cycling the flow, you're going to inject a gas that's going to push all of the brine away from your well. And that's so when you're recovering your energy, you're not sucking up brine and gas. You just want to get the gas phase that you're trying to recover. And so if you first inject CO2, that would be permanently stored. You could also use CO2 as the working phase, or you could use something else. We're looking at porous formation storage, mainly because porous formations are everywhere. The two operational plants right now are in caverns and both use air. There's actually one of those plants in McIntosh, Alabama, and the other one is in Germany. But porous formation storage is more promising because there's a much wider geographic range of places that you could use this technology. You obviously have some additional complexities though, because now you're talking about gas and brine phase interactions. If you use CO2, we know it's going to be reactive. And then what's going to happen is you have flow cycling. So one of my PhD students has been doing some simulations looking at the reactions that are going to occur at the boundary here between CO2 and brine. The CO2 right is going to dissolve into brine and form acid, and you can have dissolution of some of the phases. But actually what he's finding is that with this cyclic flow, yes, you will have some reactions near the interface, but because you're just kind of cycling back and forth, actually the extent of geochemical alteration becomes pretty limited. Over longer time scales, diffusion is probably going to play a more important role, but at least in terms of the advective dominant transport and cycling, this zone is only a couple of centimeters wide that's going to be impacted by the geochemical reactions from using CO2 in this system. Something we haven't integrated into the simulations yet are potential geomechanical effects of pressure cycling. But we've been looking at the geochemical ramifications of using the reactive fluid. You're gonna have some other kind of interesting things happening here, like some potential salt precipitation near the well, right as it starts to, in the dry out zone, you could have two-phase flow as well.
Interesting, thanks.
Mm-hmm.
Okay. Last call for questions.
Can I ask a quick question, Lauren? This is Judith Perlinger.
Sure.
So aren't these secondary minerals, when they precipitate, aren't they often amorphous? So aren't they like clogging up your pores?
So we could have some amorphous phases. Actually, we looked at the potential for amorphous silica to precipitate with our CO2 simulations, and actually it was not thermodynamically favorable. Quartz was thermodynamically favorable, which was surprising to me. I was expecting amorphous silica. What we've seen in some other systems though, I mean, in terms of what's actually going to precipitate, might be amorphous, but still understanding where the reactions will occur is a large uncertainty. So in some of my PhD work, for example, I looked at the Hanford site and we had amorphous silica precipitating on the grain surfaces, like on all of the surfaces. But it's really closely tied to coupling between the flow and reaction. And this is, you know, kind of a complicated problem. And so we don't actually know like where those reactions are going to occur. In some cases, right, we've seen it's favorable along this flow channel. In others, you know, they're preferentially occurring in, like the example that we simulated, the larger pores or the smaller pores. But really predicting that, the predictive capabilities are quite limited right now. And so that's something we're working on understanding, but there just really is not a good understanding of that at the moment.
Okay, great, thank you.
Any other questions from students? Okay, well, I guess let's virtually thank Lauren. There's an applause button.
Thanks.
Great.